Good morning to everyone, and welcome everyone to join our section for the designing and optimizing the satellite image payload. So today's discussion will discuss the workflow from the conception until the system verification using this OpticStudio. So let's start the webinar. So today's agenda, uh, first we will introducing the Ansys Optic solution and also what is the Ansys Zemax OpticStudio. And next, followed by this introduction, the satellite and imaging design challenge and also the performance. And we will split into two parts for the following section. First is the conceptual design and also start right. And the second will be the detail design and also the performance optimization. And last part will be the ensuring real world performance. And finally, we will come to this conclusion and also the Q&A section. So first will be the introduction to the Ansys. So in Ansys, we have three solutions under this Ansys Optic solution. So first one will be the Ansys numerical. So this tool is focused on the photonic component modeling. So most of the things design will be the chip level. For example, the waveguide, the sensor, and also the microsensors. So on the left will be some of the example. First one is the reflection, the internal reflection modeling in FDTD. And second, this tool will be the CMOS sensor design. And next level will be the Zemax. So Zemax is the optical lenses design and modeling. So most of the design will be the lens stack optimization and also the optomechanical tolerancing design. So we will see most of the design will be the lens design, for example, the camera, maybe the AR and VR system, and also the phone camera. And this is the metal lenses. Okay. And next one will be the system level design. We have Ansys Pure. So most of the design were related to this 3D environment integration and also the lighting and human vision perception. So you can see the design field will be the pavilion system. So it's related to the camera, and also we included the environment to this formulation. So we can like analyze the design in the system or system view. So next we'll be introducing the Ansys Optics solution for this ZBags. So the Ansys is a global leader in engineering simulation, and they provide this comprehensive suite for this photonic and optical simulation. And Zemax is one of the industry standard for this imaging system design. So in here, we need to know why Ansys Zemax OpticStudio is suitable for this aerospace design. So first is the position is the trusted by the leading space agency and aerospace company. And also second will be unified platform to design the lens design. And we also including the tolerancing wizard and also the spray light analysis tools. So it's all in one platform. And also beside the spray light, all these analysis tools, we also having this seamless integration with others Ansys physics, for example, the structural and thermal and also the fluid CFD. So all these results can be like combined with this star module to simulate the effect of the structural deformation and the thermal analysis and also the fluid the effect on our optical performance. And last one is the proven accuracy and reliability for this mission critical system. So on the right, this example is the James Webb Space Telescope, so which is NASA using the OpticStudio, which is the cloud module to analyze their design on the satellite design. So, next section we will discuss about the critical role on this satellite imaging design. So we already know the satellite we can like using for this application, for example, the Earth observation to observe the climate monitoring and also the disaster management. And next, we might using for this defense and security for the recognition and border control. And the last one will be the commercial. We can using this satellite to monitor the agriculture, maybe for the communication. So the common need for all this application will be the high resolution, the lighter weight of the satellite, and also the absolute reliability. So all here will be the like the ground scanning and also the weather station and also the communication using the satellite. So here is the challenging when the engineer they are designing this satellite things. So we will see it based on the performance versus the constraint. So for the imaging payload, we will focus on the sharper image. So we are like pushing the limit of the MTF and also the resolution to the maximum. And beside this, we also need to design the system to be lighter mass. So this one will be direct impact the launch cost. Okay. And next one, the stable performance to surviving the launch vibration and also surviving the harsh thermal environment of the space. So in the design, we also need to consider this kind of performance to like encounter all the changes in this extreme space and environment. So next one will be the straight light control. So it's like minimizing the gray and also can obscure the fan target. So most of the straight light on the space will be coming from this sunlight or the reflection of the light from others like moon or the earth or other like source. So we are like need to better control on this straight light effect. And last one will be the cost and schedule. So by using the simulation tools, we can reduce the prototyping cycle and also avoid the mission failures. Okay. So next section, I will basically discuss a simple workflow in OpticStudio. So the design in OpticStudio and also the should already arranged in the sequence. So first one will be the design interface. So we gain all the parameter inside the lens data editor and also set up all the like capture the field and also the wavelength in this system explorer. So as you can see on the right hand side will be the 3D illustration on the lenses we already key in. So this is the design module. And next one will be the analysis module. So we have a lot of the system viewer and also the image quality tools to analyze the result of the image. So as you can see here will be the export diagram and also the PSF, the point spread function. Okay. So next, after we do the analysis, so maybe the system is not as good as our expectation or it never meet our criteria. So we can using the integrated, the optimization tools. So here you can see the merit function. So we have a result. You can key in your this operand or using the automate system to create the operand for this optimization. So after we create this optimization data, we can using our optimization tools to optimize our system to get a better image quality. The next will be the tolerancing analysis. So before we sending for this manufacturing, and we need to like consider the tolerancing, for example, the misalign or the material having some degradation, or we have some offset when assembly. So all this we must consider to the design when we come to a manufacturing. Okay, so in these tools, we can like simulate all these kind of like tuning and rotating or the misalign of the lenses and also the material running off the refractive index. So from here, we can understand how best our system and is it we need additional modification on the design and according to the design and counter back this to get a better image quality. And last one will be the connect. So inside the OpticStudio, we have the programming section. So this one is using for this customize the calculation or optimization, which is the user customize. Otherwise, we can using for this repetitive simulation. So we also can using the programming to run the automation. So all the repetitive tasks we can using the program to complete it. Okay. So next one, we will come to the workflow for the titles today, which is the optical payload design for this satellite. So I will take in the example to design the Q set. So this Q set we will design from the conceptual design, which is the photo here. So it's taken from this article and also the detail optimization. We simulate or we key in all the parameter inside the lens data editor and we can come out this kind of 3D design and also do the analysis. Okay. And next we will do the small lensing analysis and followed by the straight line analysis. So straight line analysis, we will convert it into this non-sequential mode, and then we will analyze the light path using the path analysis tools. And finally, we have a system verification, which is the star module. We can include all the structural deformation and also the thermal index and also the fluid index. So all these uh, structural deformation result is from this FEA data. So the FEA data we can create using any mechanical software to do the FEA simulation. So here is one of the example we do it like importing the FEA data into the star module in Zemax. Okay, so now we will start for this part one, the conceptual design and also the starting right. Okay, so for just now the design, every design we will start from defining the system requirement and also the specification. So this is important in order to translate emission needs into an optical parameter. So for example, we will like focus on this focal length, aperture number, and also the field of view and the wavelength range. So next will be the key performance metrics such as the MTF, the spot size, and also the distortion. And also we need to decide what is the imaging sensor we want to use. So for this example, we use the 1280 by 800 pixels. So each pixel we have 3.3 micrometer and the total imaging area will be 3.84 by 2.4 mm. So on here we have the parameter to design the Q set. For example, the 3U Q set dimension is 10 by 10 by 30 cm, and the effective focus length will be 6 f 5 mm, and the wavelength range will be the visible light. And we targeted the MTF at 25% at 80 cycle per millimeter. And last one will be the capability of the design is in Leo under 700 kN, and the GST is about 9.1 meter. And all here on the right will be the parameter we will key in inside the Zemax OpticStudio. So this telescope type will be the Richard Charitian. Okay, so before we start, if we don't have any design yet or we don't have any idea, so we can start using like search the library. So on the right will be the library in Zemax. We can open it, and inside we have 642 result, which is the sample design from the others designer. So it's all collection inside the Zemax. So you can, by using the search function, you can search the parameter, and also you key in the value range to search the design you want or the lenses stack you want. Other than this method, we can using the Zemax directory. We have a sample under the sequential. You can see this telescope folder. So inside, Zemax provides some telescope design. So you also can open this design and start from this design as your starting point to create your own system. And you can optimize the system based on here. So for our first concept building, so this is a demonstration on the surface material and also the aperture setting, and do the quick analyze for the baseline performance to have a reference. So on this table, you can see is the lens data editor. So we have the surface type, or the surface we're using the standard spherical surface, and the command is like back a note about what is the lenses function. So next will be the radius design and the thickness, which is the distance of the lens or the mirror. And here we set two mirror for the primary and secondary surface. And also we don't set any coating in the initial design. And also behind here will be the conic and also the clear semi-diameter. So inside the system parameter design, we need to set the unit of the lens will be the millimeter, and the aperture is the entrance pupil diameter, which is 55 mm. And the wavelength we will choose for this FDC, which is the visible light. Okay, so for the field editor, we will key in all this analysis field for the analysis. So the view FOV here, the largest size will be the 0.38. Okay. So in part 2, we will discuss about the design for this design and performance optimization. Okay. So in the second part will be focused on this optimization and also the merit function. So initially the merit function is blank. So we can either we key in the operand inside the type here. So we can key in the operand to do the analysis. Otherwise, we can using the optimization wizard, which is this star things. So we can like select the image quality we want to optimize. And also we need to set up the pupil integration. This is the sampling. Normally we were using the circular sampling point, 3 ring and also 6 arm. And we also need to consider the boundary value for the glass and also the air, and also the maximum distortion. Finally, we just click apply. So the operand here will be auto-generate by using the optimization wizard. And on the left here, you can see beside the optimization wizard create automatically. So we also need to like doing some user customized operand, for example, to check the value, for example, the EFFL, and also the final image position, and also the thickness between the mirror 1 and also the mirror 2. So this is an optional operand, so we can define by user if needed. So from the optimization tools, we were using this global search or using the hammer talent, or we can using the local optimization tools. And also we have this glass substitution template. So we can like under the material there, if we check the soft using the glass substitution, when we doing this hammer or global search optimization, the optimizer also will help to change the material. So they will find a suitable material for the lens or the image quality. So here is some of the constraints just now we mentioned. For example, we are like control the element thickness, which is the TDHI, or the airspace. Just we also inside the visor we have the boundary, the constraint to control the airspace and also the glass space, and also like overall trace length, this TOTL, which is the entire length of your this system design, and also optimize the directly for this lightweight design without sacrificing the performance. So here is some of the analyzing image quality. The example will be the modulation transfer function, NTF, which is referred to the resolution and contrast. And second will be the spot diagram, provide the inside geometric aberration. So from here we can see the first one is the footprint, which is the cross-sectional direction to check the light ray on the mirror side. What is their footprint? And next will be the spot diagram. So as you can see, all the design is within the elliptics. So it's under the diffraction limit. And next one will be the Fourier transform, the fast Fourier transform NTF. So we will analyze the spatial frequency. So in initial design, we stated that we need about 80 cycle per millimeter, so around 25%. So this design actually is met the criteria already. Okay, so in part 3, after the optimization, then we will focus on the real world performance. So for this part, we will do is the impact of the tolerancing. So on the left will be the OPD, the optical path difference from the system design. And we need to apply like this tolerancing result. So this is the tolerancing tools. We can set up okay. So here is the setup. You can see the tolerancing data editor. We can using the preset, but if under this manufacturer, they have their preset on this tolerancing, we also can analyze based on their capability. So you can like tuning the radius, the thickness, and also the decenter and tail angles, and also the irregularity. So you can put in the limit from this factory manufacturer. So after this, you can running the tolerancing tools. So based on the sensitivity, you can compute all the tolerancing things and also the criteria. And under this tolerancing tools, we also can record the Monte Carlo to do the analysis. Okay, so you can see finally the common result will be in this kind of like sensitivity analysis. So there will come out the maximum and also the minimum, and also the value changes and criteria. So what is the merit function changes on the things already offset. Okay, so this is the system design will be the straight line analysis. So the straight line can come from the off-axis light source, like sun, moon, and earth can scatter into the imaging sensor. And this will create the gross image, wearing glare, and also reduce the contrast. And the straight line analysis is non-negotiable for high contrast imaging. So the photo on the bottom here is the example how the straight line affect our imaging detector. Okay, so on top here will be the wavelength for this infrared, and this is the optical they are sharing for this 4 IR channel for the imaging with this straight line contamination. So we can see the effect of the straight line to our imaging sensor. So next is the design, how we can like reducing this kind of stray light. So inside OpticStudio, we can convert our design into this non-sequential mode. So in under this mode, we can using first will be the auto mechanical. So we can like modeling the complex buffer and the lens mounts and also the mechanical housing. And next we will include this bidirectional scatter distribution function data for the relative surface scattering. And beside this, we also can using the anti-reflection coating. So inside the buffer and also the surface for this coating. So we can like prove our system in robust against the stray light before building the hardware directly. So next tools for this system verification will be the thermal and structural effect. So the space environment has extreme temperature gradient. So as we know this, so we will like analyze the thermal changes and also the launch root effect on our optical performance. So in this, we can do the multiphasic analysis. So in Ansys, we have Ansys mechanical. So the user can like you put in this structure into the mechanical and we run the FEA analysis. So in finally, we will get the FEA data. So the FEA data we can input into this style module and we can stick and adjust the data around the lenses region. So here is the data. When we input the FEA data, we can see our spot diagram become blur, the aberration become increase on this design, and also the NTF also drop. So, but we can using the optimization tools again when we having this kind of structural deformation or the thermal effect. So we can using the optimization tools to further analyze. So by this optimization tools, normally we will like changing the back focus of the imaging sensor, so to get a better result to and also focus the image. So here we come to the conclusion of the webinar today. So first, when using this OpticStudio, so we provide the entire design workflow from concept to validation. So this will be accelerate the development. And also we provide this high fidelity tolerancing and also the straight line analysis tools. So to ensure in-orbit success. So it's a de-risk mission. And the third one will be the optimization performance. So by using the optimization tools, we can like achieve the best possible image quality within the mass and also the volume constraint. Okay, and last one will be the simulate with confidence. So the optimization, the OpticStudio tools will rely on this integrated and also industrial proven platform trusted for this aerospace innovation. So it's quite confident and also accurate if all the parameter we key in as real. So here will be the final for the webinar presentation. So thank you for taking the time to join us for the webinar today. So for the next step, we have this free trial on student version, which is 1 year license. And we have a trial version for 30 days, full feature trial. And also if you want to learn more, you can visit this Ansys Optics website. And if you have any inquiry or request demo, you can contact us on this based on your region.